Okay, well, it's week 9 Wednesday, and tomorrow is Thanksgiving Day, so we will have no class on Friday. We have that day off. Technically, we had the lecture was made up on in week 0. That's kind of well, why we got week 0 in fall quarters to have that Thursday, Friday. But anyway, our final exam will be 1 week from Friday. So we're just going to take it in class 10th week Friday. Let me unlock this. It's always... Got it. Okay, so final exam. We'll do it 10th week Friday. So this is the plan for the final exam. It's just going to be some open-ended conceptual questions. I don't know how you guys feel about that, but no kind of calculation, no like calculus or integration or derivation or stuff. It's just going to kind of be like big picture concepts from the course. It'll cover stuff from week 1, maybe I should say week 0 to week 9. Next week, we'll look at a Gibbs sampling example, but I won't put stuff from there onto the final exam. So just stuff from week 1 to week 9, okay? And this is now I don't want to have to read like essays when I'm grading. I just want kind of like I want you to keep your answers short. The questions should be. You should be able to answer them in around like 3 sentences or less. And they're kind of just like, in my opinion, big picture ideas from the course, kind of just like the keys from the course. So, here are some example questions. What is the fundamental difference between frequentist statistics and Bayesian statistics? I don't know. I guess there's several things you can do, but I would argue the key difference is that when we're estimating unknown parameters in Bayesian statistics, those unknown parameters are treated as random variables with their own distributions. Frequentist statistics treats them as a single unknown parameter. Number 2, briefly explain how Monte Carlo estimation is performed to estimate the expected value of h of x, that is, e sub f of h of x, okay? And assume we're able to sample from the PDF f of x directly. So what would you do? How would this work? Generate a sample of random values of x from f of x, apply h of x to that sample, compute the mean, okay? Something like that. Okay. And so these are just some example problems. These are kind of the questions. Obviously, I'm not going to put these questions directly onto the final. How does the Metropolis algorithm still find the appropriate region and draw samples from, even if you give it a terrible starting location? How does that work? Well, it just continues to move towards, it accepts proposed values that have higher probability, all right, and generally moves in that direction. And so it goes. In the hierarchical baseball example, what's the hyperprior distribution for alpha and beta? The hyperprior distribution for alpha and beta are based off of omega. Omega comes from its own beta distribution. And so I think, so I have like example answers in this document. I said you can have 3 sheets of notes, writing on the front and back, as far as kind of being open note for reference, things like that. But mostly, if you get the big picture ideas, I don't know. Any questions on this regarding what the final will look like? So we'll just come in here, I'll give you a couple sheets with questions on them. You just write your answers. You'll be done. Yeah.
I just want to ask how many questions?
I said around 8 questions. About 8 questions. So that should be plenty of time. You know, that gives you what? 6 minutes per question. Okay. And probably a lot of these questions will be like either you know the answer in like a couple of minutes. You know, it shouldn't take you too long. Right? So I imagine some of you will be done in like 15 minutes, gone, and then some of you will sit and ponder. And that's also fine, okay? We'll be here. And that's that. Okay. Any other questions? Good. Okay. All right. Okay. Well, let's revisit our hierarchical model. Did I mess this up? So we were looking at kind of this baseball example, and this is the diagram that we've been looking at. All right. And what we're going to do now is we'll try using JAGs, and we specify our model. And so basically, as far as specifying the model goes, you just you put in the parameters. K is 300, A omega, B omega are 3 and 7. You say alpha and beta are based off of these things. And so anytime there's like a direct relationship, you just use the assignment operator. But then if it's a random value, so omega is drawn from the beta distribution, then you specify like this. So it looks similar to R, but it's not exactly R, okay? This is using the bugs language. And so let me go ahead and just run this script here. R2 JAGs, the beta binomial hierarchical model. And I'll share this. And the interface with R has a few nice features. I have to install that package on this machine. Let's see if this. Okay, hang on, sorry. Okay, so if we just look at some of these lines in here, again, the whole thing, the bugs model gets specified inside a function. And again, this is not a real, if you try to execute this function in R, it's going to error out, okay? But that doesn't matter. That's just kind of the container in which we transfer the model information to JAGs, okay? What we say is that every player has its own individual batting average, its own secret theta value that comes from a beta distribution. And so this value, theta, and we have, I believe we have 10 players, so we're gonna have a theta 1 through theta 10. We're gonna have 10 different values of theta, each of them drawn from this beta distribution. We say the values of y, that is whether they have a hit or an out, come from a Bernoulli distribution where the parameter is theta sub s. And then we have omega coming from here. Now notice here we're not specifying any kind of, we're not updating our values. We're just kind of specifying the hierarchical model, the structure of the hierarchical model. Okay, we're just saying the y values come from a Bernoulli specified by theta. Theta come from a beta distribution, and the beta distribution come from this omega, or are based off of this omega hyperprior distribution. Okay, we don't say that the posterior distribution of theta is going to be coming from a beta distribution with alpha plus the number of hits, or beta plus the number of outs. We're not updating those things. The JAGS, the bugs language, as it's running these samples, already takes that into account. So all we have to do is kind of just articulate the hierarchical model. We don't have to actually specify or even figure out what the posterior distributions look like. Let me just check it over here. Okay, so we have that going. So we have that, okay? So here again, I'm going to simulate my data. I'm going to say set seed 1. We've got 10 players. I'm going to draw 10 imaginary batting averages. So these are different batting averages for 10 different players. This person bats 252. This person bats 275. We're going to say the number of at-bats varies. So some players have more at-bats or fewer at-bats than others. We're going to build up a matrix, and we're going to fill in the hits, okay? So I'm saying for each player, I want to get the hits are either going to be 1 or 0. Okay, so I'm saying R binom. So when you do R binom, so let's say I want 10 of these things. We're going to do 1, and we want, let's say 0.3, okay? Oh, there I got a bunch of zeros, okay? Sometimes you get zeros and ones and things like that. And so each of these things, we've got maybe 400, 500 of these things. And my matrix, however, my big matrix Y, remember each of these players have different numbers of hits. My entire matrix has a width of 521. And that's because when I looked at the number of at-bats, the biggest number I have is 521. Okay? And so I'm going to pad these with NAs. Right, so this person only has 486 at-bats. So if we look at the first row, okay, we've got 486 at-bats. But then we have a whole bunch of NAs so that the entire length ends up being 521. Okay. And I do this for each of the players. Some of the players have more at-bats than others. This one had 7 more at-bats. Okay, so I'm going to go ahead and just kind of fill out my entire matrix as such. We can calculate the total number of hits and the total number of at-bats. So the total number of hits is 118, the total number of at-bats is 486. And kind of the batting averages that we've seen here are something around here, 0.242, and so on for each of these players. Okay, so what we're going to do is we're going to specify the JAGS model as I've written in those slides. We say each player's batting average, each player's theta comes from a beta distribution. The hits, the outs, each individual one, so I have a loop within a loop, where this applies to player row S, column J, for J through the number of at-bats. Those are Bernoulli things, okay? And the omega comes from this hyperprior distribution. So we list that off, okay? in order for this JAGS model to work, we need to specify these values, the number. So all of these things, the JAGS model will be able to figure out everything that we've given it. So K is 300, so it finds that. B omega is 7, 8, 3 and 7. Omega comes from here. But it's going to say, hey, well, where do I get the number of at-bats? Where do I get the number of players? Because these aren't defined anywhere. Okay, and then where do I get these values at Y? Okay, so those aren't defined anywhere, so we got to kind of gather the names of the things that exist in our global environment, right? So Y is this big matrix. The number of at-bats is just this vector, and the number of players is just 10. Okay, we could have specified these directly in here, but this is what we have. So these we gather together in this list. We tell the JAGS system that these are the parameters that we want to keep track of. Theta, and we have 10 theta values, and omega. We got 1 omega value. So we'll do that. We start off with some initialized values. So here for the initial values, I'm just going to draw 10 random beta values from this distribution. For omega, I'm going to draw 1 random beta value from this distribution. Now, it doesn't matter what these numbers actually are. It's just kind of an initial starting value, right? So because we're just running the sampler, and you can have different starting locations. And so here we're going to just kind of do this. Again, it's specified in a function. And again, the function is just kind of a wrapper. It's a little bit weird interacting with this, but you specify it in there. Okay, and so now I'm just going to let it run. Okay, we're going to call JAGS. We say the data comes from this list of things, the data JAGS. The initialized values come from here. The parameters to save are theta and omega. We're going to say run 3 chains, run 15,000 iterations, throw away the first 1,000. That's going to be our burn-in period. And the model file base.mod is the function that wraps up the thing. So I'm going to go ahead and just run that. Whoops, could not find function JAGS. Failed to locate. Oh dear. You know what? I'm sorry. This is embarrassing. I have it loaded on my desktop computer at home, but I didn't install it on my laptop here. Okay. Okay, let me pause this video. Okay, I think it works now. Let's try this again. So now I've finished installing JAGS on the machine. Okay, so now it's running. And we get a little progress bar, which is nice, just because sometimes these give samplers can take a while. Okay, and it is done now. I don't know what all of this stuff says. Compiling model graph. Okay, so we stored the results of the JAGS fit into Bayes model fit. So if I print this out, this tells me what it has found. So again, we have 10 theta values and 1 omega value, and each of these has its own random distribution, right? Probability distribution. And so it's giving us some summary information. It's giving us kind of what the median of each of these values are. All right, and it also gives us kind of the lower, 25th percentile, 75th percentile, and things like that. And we can kind of take a look. And so let's just, again, the number of hits, the number of at-bats is here. I could just do kind of y over n, and we can compare how did the 50th percentiles compare with these actual values. So we have 0.242 versus 0.258, 0.281 and 0.281. 0.238 to 0.256, 0.296 and 0.291. And the highest over here is 0.315, gives me a theta 9 of 0.303, and 0.303 corresponds to kind of 0.296 over here. And the total omega is at 0.281. I can do the sum of y. This is kind of my estimated omega would be 0.282. We're right around there, 0.281. You can get a bit more. Let me click. If you just call plot, it gives you, maybe this is not as useful here. It gives you a little bit of a kind of it. It says 80% confidence intervals for each of these different values. So we have 10 different theta values. We've got one omega value. You can also ask for the trace plots, right? And this is going to be, there's a whole bunch of these that are going to pop up. So let me just expand this over here. Okay. The deviance is just kind of all over the place. But so this is, we have three different traces, a red, a green, and a blue line. And again, what we kind of want to see is like random values all over the place, which is what we are seeing here. Theta 1, theta 2, theta 3. So these all look like we have pretty good IID random values drawn from here, right? So if you remember in one of the earlier lectures, we were talking about your metropolis algorithm, and if you can kind of trace it, then maybe your values are too correlated. If you get kind of stuck in these flat areas, it's also not a good sign. Yeah, Ethan. What are the what? Oh, I ran 3 simultaneous Gibbs samplers. Okay, so we ran them kind of these parallel sampling things, or we ran the sampler 3 times. Okay, we also have these diagnostic plots that can be loaded with these libraries. So you can take the Bayes model fit, convert it into an MCMC object, and you'll get a series of, did that not work? Okay, this is a little bit difficult to see. So we have kind of all of the trace plots from 0 to 15,000, and they're all kind of just all over the place. Fine. You can get the resulting density plots as well. For some reason it's not. Okay, I've got to call it twice for it to work here. And so you end up getting struggling. There we go. Can I redo it? So theta 1 is centered a little bit over, looks to be centered around 0.26. And you can see kind of the resulting density plots from the 3 different traces. They're all very similar, okay? With the exception, I mean, not really, there's no real exceptions here, but you can kind of see the blue, the purple, and the dark green, and they all kind of overall have some very similar densities resulting from the samples that they've drawn. And it's hard to see any difference just because they're all centered, but if you pay attention to where the center of these things are, so this one's centered at around 0.31, this one looks to be centered around 0.28, 0.305, this also looks to be around 0.28, okay? And this one's around 0.26. So you can see kind of some of these different distributions. Omega is centered, right at 0.281. It has a smaller amount of spread compared to the other distributions. Yeah.
How come it's like not in order? Like beta ups,
Why aren't these in order? Yeah, I don't know. It's a little bit arbitrary. I don't know how it decided to plot these things in what order. I'm not sure. It's weird. Yeah, it's not even in any order that really makes sense, right? Maybe alphabetical. It's alphabetical from the bottom. Theta 1, theta 1, 0, theta 2, theta 3, theta 4, 5, 6, 7, 8, 9. It's alphabetical, where it goes 1, 1, 0, 2. So, okay. This is almost the exact same thing. Here I've just specified the model ever so slightly differently. So if you look at this model specification versus this model specification, here I'm modeling, in the original model, I modeled the hits as zeros and ones, the actual hits as zeros and ones, and each one is a Bernoulli. Over here, I just have a vector of hits, okay? Y is just a vector of the total number of hits. And here we're going to say the total number of hits, 118, comes from the binomial distribution, the number with the batting average parameter, probability parameter theta s, the number of at-bats over here. So this is just another way to specify it. I don't know if I actually want to run it. I mean, I can. It's not hard. So pretty much the same thing. It's going to run. I think we're going to get the same results just because it's based off of the same data. So if I look at these numbers, again, these are just, this is a random sample. So one of the reasons why our plots, these plots, it's hard to get them. But when we looked at those trace plots, one of the reasons why the trace plots looked so good is because we have quite a bit of thinning going on. So when you did the Metropolis algorithm, I just had you plot the values directly. Okay, so the trace plot, it's a little bit hard to see, but you might actually be able to follow them around, but then if you look at these things over here, okay? Here, these are just kind of the 1,000 values that we've saved. It says iteration, but it's kind of the 1,000 values that we've saved. And it says, we ran 3 chains, 15,000 iterations. The first 1,000 are discarded, okay? And then we were thinning them by a factor of basically 14. So we did 15,000 iterations, but basically out of every 15, 14 of them are discarded. So we're only kind of keeping 1 out of 15. And so each value that we're keeping, by the time we do 15 iterations later, it's really going to feel like independent from the previous one, right? If you keep every single value, the next value we know is going to be correlated or with the previous values. But then if you go 15 iterations later, it's going to feel quite a bit different, right? Kind of like if you think of yourself and your parents, there's probably a lot of things in common between you and your parents, right? But then if you go back 15 generations, we can't even comprehend that far back, but if we go back, several generations, or if you think of, cousins that are multiple generations away, it might feel like you are fairly independent of each other, right? There's you're both, there's a relation there, but also very, very much independent, or close to being independent. So So that's what we see here, okay? Plotting this. This model, okay? I've just kind of put a whole bunch of these different models here. This one models K. So earlier we had K with, we specified it as 300. If you wanted to model K as a random variable, you can do that. And here I just arbitrarily chose a gamma distribution with shape parameter 2 and rate parameter 0.008. And that gives us kind of a wide, like if I do, how do you plot the gamma distribution? What is my plot function? Okay, so this would be like a gamma, a d gamma here, okay, where it looks to be a peak of around 100 something, 125 maybe, I don't know. The mean, I think, is, what's 2 divided by 0.008? 250. With a mean of 250, obviously we can end up having bigger or smaller gammas values here. Okay, so here's just another function, and again, you can kind of specify any of these variables to be a random thing, however you want. Okay. And just basically your hyper prior parameters are the only ones that now get specified. And here we're specifying them as 3 and 7. And so they can end up quite a bit all over the place. Okay. Well, anyway, that's just using JAGs. If this is really just a very, very short introduction to it. I would, okay, my microphone just died. Just look up R2 JAGs. Read the documentation here. The reference manual is going to give you some good examples, I think. And you can probably also just look for R2 JAGs tutorials. Okay. And so even though JAGs itself is not really being updated frequently, the R2 JAGs package is still very current. And the kind of the framework for JAGs hasn't needed updating in several years. Okay. Although the another Monte Carlo package is gaining popularity called Stan. I haven't learned it yet, so I'm not confident enough to kind of introduce and teach it to you guys. But that's another thing there. Okay, and all of the R2JAGs GitHub is available here as well. Okay. All right, we'll end here for today. Have a good weekend, you guys. Have a happy Thanksgiving, and then next week we'll do maybe a fun example of the Gibbs sampler for kind of this document clustering model, which could kind of be fun. Again, it's mostly for fun. I've got a homework assignment related to it. Coming up, so I will share that with you guys next week, and then yeah, for the final exam, it's just going to be some conceptual questions covering content from the beginning of the course. Okay, have a good day, you guys. Have a Nice Thanksgiving. We'll see you guys on Monday. Yeah, question.
No view today.
Yeah, no view quiz today. So we'll see you guys later.